Right now, there is a region on the Sun's surface large enough to swallow Earth several times over. It's facing us, it's active, and if it erupts in the next 48 hours, we could be looking at something that fits what risk analysts call a black swan event: rare, unexpected, and potentially devastating. This is about an active region that produced a significant eruption on New Year's Eve, and now scientists are monitoring whether additional eruptions could occur while Earth is still vulnerable. What makes this different from every solar storm warning you've ever heard is that this time, the timing couldn't be worse. Stay with me for the next few minutes, because we're going to unpack exactly what's happening on the Sun right now, why scientists are watching this particular sunspot with unusual intensity, what makes this a potential black swan event that could disrupt modern life in ways most people haven't considered, and most importantly, what the next 48 hours could mean. The sunspot we're talking about has a designation. Scientists call it AR4324. That combination of letters and numbers might sound technical and cold, but what it represents is anything but ordinary. Right now, as you're watching this, AR4324 is churning with magnetic energy on the Sun's surface. If you could see it with your own eyes through proper solar filters, it would appear as a dark blemish against the blazing brightness of our star. But that darkness is deceptive. What looks like a dark spot is actually a region where the Sun's magnetic field has become so twisted and concentrated that it's cooler than the surrounding surface. And when I say cooler, I mean relatively speaking. We're still talking about temperatures that would vaporize anything we know. But here's what matters. That magnetic complexity, that twisting and churning, is a loaded spring. It's potential energy waiting for release. And when that release happens, it doesn't whisper. It explodes. The scale of what we're dealing with is difficult to grasp because our human brains aren't wired to process numbers this large. AR4324 is massive. If you could pick up Earth and drop it into the middle of this sunspot, you could fit our entire planet in there multiple times over. Think about that for a second. Everything you know, every city, every ocean, every mountain range, every person who's ever lived. All of it could fit into this active region multiple times. That's not the scary part, though. Large sunspots exist all the time. The Sun is constantly covered in them during active periods of its cycle. What makes AR4324 different, what makes it worth talking about right now, is not just its size, it's the type of magnetic structure it's developed. Scientists classify sunspots by their magnetic configuration, and AR4324 has what's called a beta-gamma structure. You don't need to remember that term, but you need to understand what it means. It means this sunspot has multiple magnetic poles crammed together in a chaotic arrangement. Imagine trying to push the same ends of several magnets together. They want to repel, they want to snap apart. That tension, that magnetic pressure, is what we're seeing in AR4324 right now. And when that tension releases, when those magnetic fields finally snap like overstretched rubber bands, the energy that gets thrown into space is staggering. The energy release from a major solar flare can be equivalent to millions of powerful explosions. But here's where it gets personal. AR4324 isn't sitting on the far side of the Sun where we'd be safe. It's not pointing away from us into the void of space. It's facing Earth. Directly. Right now. The Sun rotates, and sunspots move across its face from our perspective, and there's a window of time when a sunspot is in the danger zone, when an eruption would send all that energy and material straight toward us. We're in that window right now. For the next 48 hours, maybe a little longer, AR4324 is in prime position. If it erupts during this time, there's no dodging it. There's no safe angle. It's positioned where an eruption would be directed toward us. Now, let me be clear about something, because I want you to trust what I'm telling you, and trust comes from honesty. Most sunspots don't erupt. Most of the time, even complex active regions like this one just simmer and churn and eventually fade away without incident. The Sun has active regions all the time during solar maximum, which is where we are right now in the 11-year solar cycle. So the existence of a big complex sunspot isn't automatically cause for alarm. Scientists see them frequently. What changes the equation is context, and that's where this story takes a turn that most people haven't heard about yet. This is where the term black swan comes in, and if you're not familiar with that phrase, don't worry. We're going to dig into exactly what it means in a moment, but for now, just understand that a black swan event is something rare, something unexpected, something that has massive consequences precisely because nobody saw it coming, or because all the wrong conditions lined up at once. It's the financial crisis nobody predicted. It's the pandemic that shut down the world. It's the perfect storm that wasn't supposed to happen. And in the context of space weather, a black swan event would be a solar eruption that doesn't just hit us, but hits us when we're already vulnerable, when our defenses are down, when the timing creates compounding effects that a normal solar storm wouldn't cause. Here's the thing most people don't realize about Earth's relationship with the Sun. Earth has natural protection systems. Our planet has a magnetic field, an invisible shield that wraps around us and deflects most of the solar wind and radiation that streams off the Sun constantly. That magnetosphere is our first and best defense against space weather, when a solar storm hits. When a blast of charged particles and tangled magnetic fields slams into Earth's magnetic bubble, there's a battle. Usually our magnetosphere holds. It flexes, it compresses, it channels energy toward the poles where we see auroras, but it protects us. The systems we've built, the satellites in orbit, the power grids on the ground, they experience stress, but they survive. That's what happens under normal circumstances. But what if circumstances aren't normal? What if our magnetosphere is already under pressure when the next hit arrives? What if Earth's shield is already flexed and strained and pushed to its limits, and then a second massive blow lands before we've recovered? That's not a normal solar storm. That's a compound event, that's 2 punches instead of 1. And the difference between those 2 scenarios isn't additive, it's exponential. The damage doesn't just double, it multiplies in ways that are hard to predict and harder to stop. That's the black swan scenario. That's what scientists are quietly concerned about right now. Because here's what you need to know, and this is the part that changes everything. Earth is currently experiencing geomagnetic storm conditions. Our planet is facing a solar storm now that started on New Year's Eve. On December 31st, the Sun released a powerful flare, and with it came a coronal mass ejection, a billion-ton cloud of plasma and magnetic fields that travelled through space for 2 days and has been impacting our magnetosphere since January 2nd. This isn't speculation, this is happening. Forecasters issued geomagnetic storm watches. Aurora chasers in northern regions are outside with their cameras. The storm is here, and while it's not catastrophic, while it's not bringing down power grids or knocking satellites out of the sky, it's real. Our magnetosphere is flexed, our defenses are engaged, we're already taking a hit, and that's where AR4324 comes back into the picture. That's where the 48 how countdown becomes critical. Because if this massive, complex, energetically loaded sunspot erupts in the next 2 days, while Earth is still reeling from the current storm, while our magnetosphere is already responding to the first disturbance, a second CME impact during this recovery period would have amplified effects. Think of it like successive waves hitting a shore. The second wave arrives while the water from the first is still receding, creating a higher combined effect than either wave alone would produce. And in the context of our technological civilization, that could mean the difference between an inconvenient disruption and a cascade of failures that takes weeks or months to fully repair. This is not about fear, this is about understanding. It's important to understand what's happening with current solar activity, what makes compound geomagnetic storms different from single events, and why scientists are monitoring AR4324 closely during this recovery period. And over the next several minutes, we're going to walk through exactly what a black swan event means, what the science behind this threat actually looks like, what happened the last time conditions like this aligned, and what scientists are watching for as this window ticks down. But before we go deeper, I need you to do something. If this information matters to you, if understanding real threats and real science is something you value, hit that like button right now. Subscribe to this channel so you don't miss updates as this situation develops, because if AR4324 does erupt, you're going to want to know what happens next. And drop a comment telling me where you're watching from, because where you are on this planet matters when it comes to space weather impacts. Some regions may experience different effects than others. Some power grids are older and less protected. Some latitudes see effects that others don't. So tell me, where are you right now? What part of the world are you calling home as we watch this unfold together? Because that's what we're doing. We're watching this together. Scientists are monitoring, spacecraft are recording, forecasters are analyzing, and all of us, everyone on this planet, we're living through the same 48-hour window, observing whether AR4324 will produce any significant activity. But here's what makes this different from every other solar threat you've heard, hyped up, and forgotten. This isn't about one factor. It's not just a big sunspot, it's not just a current storm, it's about convergence. It's about multiple risks overlapping in a narrow window of time. And that convergence, that alignment of conditions that rarely happen together, is what transforms a routine space weather event into what risk analysts call a black swan. So let's understand what this means, where it comes from, and why it's the perfect description for what we might be facing in the next 2 days. The phrase black swan might sound poetic, even a little mysterious, but it comes from a very specific place in how we think about risk and probability. For most of human history, people in Europe believed all swans were white. Every swan anyone had ever seen was white. It was a fact, a certainty, something you could bet your life on. White swans were just how swans were, and then explorers reached Australia and discovered black swans. The impossible was real, the unthinkable existed. And suddenly, every assumption built on the certainty of white swans had to be reconsidered. That moment of shock, that realization that what you thought was impossible can actually happen, is the core of what we now call a black swan event. The modern use of the term comes from a thinker who studied financial markets and risk. He noticed that the largest disruptions, the ones that caused major economic impacts and toppled institutions, weren't the predictable ups and downs that everyone prepared for. They were the shocks nobody saw coming. They were the events that fell, outside the normal range of expectations, the ones that seemed so unlikely that planning for them felt like paranoia. But when they happened, their impact was enormous. And here's the critical part. After they happened, after the dust settled and people looked back, suddenly the event seemed obvious. People would say, "We should have seen this coming, all the signs were there." But in the moment before it happened, it was invisible. It was unthinkable. That's a black swan. Rare, unexpected, massively impactful, and only obvious in hindsight. Now, you might be thinking about examples from recent history. The financial collapse that ripped through the global economy and destroyed retirement accounts and threw millions out of work. That was a black swan for most people. Experts had warned about housing bubbles and risky debt, but the scale and speed of the collapse took almost everyone by surprise. Or think about the pandemic that shut down the world. Scientists had been warning for years that a global pandemic was possible, even likely eventually. But when it actually arrived, the timing and the specific virus and the cascading effects on supply chains and society caught almost everyone unprepared. These are black swans. Not because they were completely impossible, but because the specific convergence of factors that made them happen seemed so unlikely that most people didn't take the threat seriously until it was too late. So how does this apply to the sun? How does a star that's been burning for billions of years, that we've been studying intensely for decades, that we monitor with satellites and ground stations and mathematical models, how does that star produce a black swan? The answer is in the convergence. It's not about the sun doing something it's never done before. The sun erupts all the time. Solar flares happen daily during active periods. Coronal mass ejections are routine. We've seen them. We've measured them. We've weathered thousands of solar storms without civilization collapsing, so a solar eruption by itself isn't a black swan. It's expected. It's normal. It's what the sun does. But what if that eruption happens at exactly the wrong time? What if it happens when Earth's defenses are already weakened? What if it happens when our technology is particularly vulnerable? What if multiple factors that usually don't align all come together in a narrow window and create a compound threat that's far worse than any single element would be on its own? That's when a routine solar event transforms into a black swan. It's not about the size of the eruption, though that matters. It's about the context. It's about timing. It's about the convergence of conditions that rarely overlap. Let me give you a simple analogy. Imagine you're driving down a familiar road. You've driven it 1,000 times. You know every curve, every pothole. Most days that road is safe. But what if one day there's black ice that you can't see? And what if at the same moment your tyre pressure is low because you've been meaning to fill it but haven't gotten around to it? And what if a deer jumps out right when you hit that patch of ice? Any one of those factors alone you could handle. You've handled them before. But all three at once? That's when a routine drive becomes a wreck. That's convergence. That's when independent risks multiply instead of add. That's what we're looking at with AR4324 and the current geomagnetic storm. The sunspot is one factor. Its magnetic complexity is another. The fact that it's Earth-facing is a third. The fact that we're already under storm conditions from the New Year's Eve eruption is a fourth. And the fact that we're in solar maximum when the sun's background activity is elevated and unpredictable is a fifth. Any one of these on its own is manageable. We deal with sunspots all the time. We deal with geomagnetic storms regularly. But when they all overlap in a 48-hour window, when the second punch comes, while we're still off balance from the first? That's when you move from routine space weather into black swan territory. And here's why this matters more than just an intellectual exercise in risk theory. Black swan events are, by definition, the ones we're least prepared for. They're the scenarios that don't get drilled. They're the contingencies that don't get funded. They're the warnings that get dismissed because they seem too unlikely, too expensive to prepare for, too much like paranoia. When budgets get tight, you don't spend money on the disaster that probably won't happen in your lifetime. You prepare for the routine threats, the everyday challenges, and that's rational most of the time. But it means that when the black swan actually arrives, when the improbable becomes real, the systems we've built aren't ready. The redundancies aren't in place. The backup plans haven't been tested. And that's when small failures cascade into big ones. This is not about panicking. This is about recognizing a specific type of threat. Most solar storms are not black swans. Most of the time, even during solar maximum, even with complex sunspots and fast coronal mass ejections, Earth's natural defenses and our engineered systems hold. We see beautiful auroras, we get some radio disruptions, maybe a satellite has to maneuver, but life goes on, the lights stay on, the internet keeps working, GPS keeps guiding your phone's map. That's the normal scenario, and it's the most likely outcome even now. But the possibility that we're in a scenario where multiple risk factors overlap, creating potential for a more significant geomagnetic storm than usual, is based on scientific monitoring and historical precedent. That's not a conspiracy theory. That's a risk assessment. That's looking at multiple factors and recognizing that when rare conditions overlap, the outcome can be disproportionate to what you'd expect from any single factor. And the honest truth is that we've never had a major compound solar event during the era of modern technology. We've never tested what happens when our satellite constellations, our GPS networks, our interconnected power grids, our just-in-time supply chains, our cloud-dependent everything gets hit by a black swan solar storm. We have models, we have simulations, we have educated guesses, but we don't have real-world experience. And that uncertainty is part of what makes this a black swan scenario. So when I say AR4324 could trigger a black swan event if it erupts in the next 48 hours, I'm not saying the sun is going to do something impossible. I'm saying the timing is such that a normal solar event could have abnormal consequences because of the specific conditions we're facing right now. I'm saying that the convergence of factors is rare enough that most of our preparedness is built around scenarios where these factors don't all line up at once. And I'm saying that history shows us again and again, the disasters we're least prepared for are the ones that hurt the most. But to really understand why this matters, why scientists are watching this particular moment with more attention than usual, we need to dig into the timing complication. We need to understand what's already happening to Earth right now today as you're watching this. Because that's the piece of the puzzle that transforms a routine sunspot watch into a potential black swan scenario. That's the factor that changes the equation from interesting to urgent. So let's talk about what Earth is dealing with right now, why our defenses are already engaged, and what that means for the next 2 days. Here's the part that most people watching this video probably don't know yet. While you were celebrating New Year's Eve, while you were watching fireworks or toasting with friends or just trying to survive the transition from one year to the next, the sun was putting on its own show. On December 31st, a powerful solar flare erupted from the sun's surface. Scientists classified it as an M-class flare, specifically an M7.1, which puts it in the upper range of medium-strength eruptions. It wasn't the biggest flare the sun can produce. X-class flares are stronger, but M7.1 is nothing to dismiss. It's powerful, it's energetic, and it came with something that matters even more than the flare itself. When that flare erupted, it launched a coronal mass ejection. Imagine a billion-ton cloud of plasma, superheated gas that's so hot the electrons have been stripped from the atoms, mixed with tangled magnetic fields, all of it thrown off the sun's surface and hurled into space at tremendous speeds. That's a CME. It's not the light and radiation from the flare, which reaches Earth in 8 minutes. It's the physical material, the mass, the substance of the sun itself being thrown outward. And when that CME was launched on New Year's Eve, the trajectory calculation showed it was heading toward Earth. For 2 days, that cloud of plasma travelled through the void between the sun and our planet. 2 days of crossing 93 million miles of space, carried by the momentum of the eruption and the push of the solar wind. And on January 2nd today, that CME arrived. Right now, as you're watching this, Earth's magnetosphere is being hammered by that cloud. The impact started in the early hours of the second and continues as we speak. This is not speculation. This is not a warning about something that might happen. This is happening right now. The official space weather forecasters, the scientists at NOAA's Space Weather Prediction Center, who monitor these things around the clock, issued geomagnetic storm watches for January 2nd and 3rd. They're expecting G1 to G2 storm conditions, which translates to minor to moderate impacts. At these levels, we see effects. Auroras are visible at lower latitudes than usual. People in northern states who don't normally get to see the lights might step outside tonight and catch a glimpse of green or red curtains dancing in the sky. Radio communications get disrupted, especially at high frequencies. Satellite operators have to watch their systems more carefully because the increased radiation can cause anomalies or even damage sensitive electronics. Power grid operators see fluctuations, induced currents in long transmission lines that require monitoring and sometimes mitigation. But here's the critical point. G1 to G2 storms are manageable. We deal with them regularly during solar maximum. They're disruptive but not catastrophic. The lights don't go out, satellites don't start falling from the sky, GPS doesn't stop working. Our systems are designed to handle this level of stress. We have protocols, we have redundancies, we've weathered thousands of storms at this level and come through just fine. So why am I spending time talking about a routine geomagnetic storm from a New Year's Eve flare? Because of what it means for Earth's magnetosphere right now. Think of Earth's magnetic field as a shield. That's not just a metaphor, it's a functional description of what it does. The magnetosphere wraps around our planet in an invisible bubble, extending tens of thousands of miles into space on the sunward side and stretching even farther on the night side in a long tail. When the solar wind flows past Earth constantly, our magnetosphere deflects it, channeling most of that stream of particles around us like water, flowing around a rock in a river. That's the baseline. That's normal conditions. But when a CME hits, when a dense cloud of plasma with its own tangled magnetic field slams into our magnetosphere, the interaction is violent. The CME's magnetic field can connect with Earth's magnetic field in a process called magnetic reconnection. When that happens, energy transfers, the magnetosphere compresses. The boundary between our protective bubble and the solar wind gets pushed inward. The whole system flexes and strains under the pressure. Inside the magnetosphere, particles get accelerated and funneled down toward the poles, which is where auroras come from. They're beautiful, but they're also a sign that our defenses are being tested. They're evidence of energy pouring into Earth's magnetic environment. Now, the magnetosphere is resilient. It's been protecting Earth for billions of years. It's weathered countless solar storms, some far worse than what we're experiencing right now. It recovers. After a CME passes, after the pressure eases, the magnetosphere relaxes back toward its normal shape. The compressed boundary expands again. The particle populations settle. The system returns to equilibrium. But that recovery takes time. It's not instantaneous. After a significant geomagnetic storm, Earth's magnetic environment can remain disturbed for days. The particle belts around our planet can stay enhanced. The whole system can remain more sensitive, more reactive to new disturbances, and that's where we are right now, today, January 2nd. Earth's magnetosphere is not at rest. It's not in its relaxed state. It's engaged. It's compressed. It's dealing with the ongoing impact of the New Year's Eve CME, and this is the setup for the Black Swan scenario. This is the timing complication that transforms AR4324 from just another interesting sunspot into something scientists are watching with unusual intensity. Because if AR4324 erupts in the next 48 hours, if that massive, complex, magnetically loaded active region releases its energy while it's still facing Earth, the CME that results would arrive at our planet potentially within 24 to 72 hours depending on its speed. Fast CMEs, the ones driven by the most powerful eruptions, can make the journey in less than a day. They've been clocked at speeds that would cross the Sun-Earth distance in 15 to 18 hours. That means an eruption tomorrow could result in a CME impact as early as the day after, or possibly even sooner. And here's the critical calculation. If that second CME arrives while Earth is still recovering from the first one, while our magnetosphere is still compressed and stressed and hasn't had time to fully relax, the impact of the second hit is not the same as it would be under normal conditions. This is not simple addition. This is not CME1 plus CME2 equals twice the impact. When you hit a system that's already strained, the effects multiply. The magnetosphere doesn't have its full capacity to absorb and deflect. The particle populations inside the magnetosphere are already enhanced, which means there's less room for new particles before you reach dangerous levels. The currents in Earth's ionosphere are already flowing, which means additional currents can push systems past their breaking points. Think of it like a rubber band. If you take a rubber band and stretch it once, it handles the strain, it stretches, it holds, you let go, and it snaps back. That's a normal solar storm hitting Earth's magnetosphere. But what if you don't let go? What if you keep that rubber band stretched and then you pull it even farther? Now you're in territory where the material is stressed beyond its normal limits. Now you're approaching the breaking point. That second pull, that additional strain while the rubber band is already extended, that's when things snap. That's when failures happen that wouldn't occur under single event conditions. We have historical evidence for this. We've seen compound solar events before. The Halloween storms of October 2003 were a series of massive eruptions that hit Earth in rapid succession over about 2 weeks. Multiple X-class flares, multiple fast CMEs, each one hitting while Earth was still reeling from the previous impact. And even though our technology was less advanced and less vulnerable back then than it is now, we still saw serious effects. Satellites were damaged, some were permanently lost. Power grids experienced issues. The Swedish grid had voltage, swings that could have caused blackouts if operators hadn't intervened. GPS systems were disrupted. Airline flights had to reroute to avoid increased radiation exposure at high altitudes. And that was in 2003, when we had a fraction of the satellites we have now, when GPS wasn't embedded in every device we carry, when our power infrastructure wasn't as interconnected and complex. Go back further to March 1989. A single powerful geomagnetic storm hit Earth following a solar eruption. The storm caused the entire Quebec power grid to fail. 6 million people lost power for 9 hours. Transformers were damaged. The recovery took days beyond just restoring service. And that was from one storm, one hit, under conditions where Earth's magnetosphere wasn't already compromised by a previous event. Imagine if that storm had arrived during an existing disturbance. Imagine if Quebec's grid had been struggling with fluctuations from an earlier impact and then got hit with the full force of the March 13th storm on top of those existing stresses. The damage could have been far worse. The recovery could have taken weeks instead of days. That's the scenario we're potentially looking at now. That's why the next 48 hours matter so much. It's not just about whether AR4324 erupts. It's about when. It's about the timing. Because an eruption next week, after Earth's magnetosphere has had time to recover from the current storm, after the particle populations have settled and the magnetic boundaries have relaxed, that eruption would be dealt with as a standalone event. Serious potentially if the eruption is strong enough, but standalone. Our systems would face it at full capacity, but an eruption in the next 2 days while we're still under storm conditions, while our defences are already engaged and strained. That's the compound threat. That's the 1-2 punch. That's when you move from manageable to potentially critical. And the honest truth is we don't have extensive real-world data on how modern systems respond to this kind of rapid succession compound event at scale. We have simulations. We have models. Scientists have studied historical cases and tried to project what would happen with today's technology. But projections are not the same as experience, and this is where the black swan concept comes back. Because if we haven't experienced it, if we haven't tested our systems under these specific conditions, if the convergence of factors is rare enough that our planning and infrastructure aren't built to handle it, then by definition we're less prepared than we think we are. We're vulnerable in ways we might not fully understand until the moment it happens, and that gap, that difference between what we think our systems can handle and what they actually can handle under unprecedented conditions, that's where black swans live. That's where the unexpected massive impact comes from. So yes, Earth is currently experiencing geomagnetic storm conditions. Yes, we're managing the current storm, but the real question isn't whether we can handle the storm we're in right now. The real question is whether we can handle another one on top of it before we've recovered. And for that question, we need to look at what actually happened the last time conditions like this aligned. We need to learn from history, because history is the only teacher we have when it comes to rare events. So let's go back and examine the moments when the sun reminded humanity that we're not as invincible as we like to think. If you want to understand what a compound solar event can actually do, you need to go back to October 2003. The sun was in an active phase of its cycle, not unlike where we are now. Halloween was approaching, and over the span of 2 weeks the sun threw everything it had at Earth in what became known as the Halloween storms. This wasn't a single event, this was a barrage. Multiple active regions on the sun erupted in rapid succession. X-class flares, the most powerful category, erupted one after another. Some were among the strongest flares ever recorded, and with those flares came fast, powerful coronal mass ejections, multiple CMEs racing toward Earth with less than a day between arrivals. The first major hit came on October 28, 2003. A CME from a massive flare slammed into Earth's magnetosphere and triggered one of the strongest geomagnetic storms in decades. Power grids around the world saw induced currents. In Sweden, voltage fluctuations were so severe that operators had to take emergency action to prevent blackouts. Transformers were at risk. In the United States, grid operators watched their systems carefully, managing loads and monitoring for damage. But that was just the beginning, because less than 24 hours later, while Earth's magnetosphere was still disturbed from the first impact, another CME arrived, and then another over the following days. The compound nature of the Halloween storms is what made them so significant. Each individual CME might have been manageable on its own, absorbed and deflected by Earth's magnetic defences with limited damage. But coming in a rapid succession, each impact landing while the magnetosphere was still recovering from the previous hit, the cumulative effect was far greater than any single event would have been. Satellites started experiencing problems, anomalies multiplied. Some satellites went into safe mode, shutting down non-essential systems to protect themselves. Others suffered permanent damage. Japan lost a scientific satellite entirely. The radiation environment in space was so intense that astronauts on the International Space Station had to move to more shielded areas of the station. Flights that normally routed over the poles had to be diverted because radiation exposure for crew and passengers exceeded safe limits. GPS systems, which the world had become increasingly dependent on by 2003, experienced widespread disruptions. The signals were degraded, accuracy dropped. In some regions, GPS was effectively unusable for hours. Imagine that today. Imagine every phone that relies on GPS for maps and location services suddenly losing accuracy or connection. Imagine every shipping container, every delivery truck, every precision agriculture system that depends on GPS timing signals suddenly working with degraded or missing data. In 2003, we survived those disruptions because our dependency wasn't as total as it is now. But the vulnerability was already apparent, and then there's the most famous historical case, the one that every space weather scientist references when talking about what the sun is capable of. The Carrington Event, September 1859. The world was a different place. Electricity was a novelty. There were no satellites, no power grids in the modern sense. The most advanced electrical technology was the telegraph system, networks of wires connecting cities and countries, carrying messages in Morse code. On September 1, 1859, British astronomer Richard Carrington observed a massive solar flare. The sun erupted with what we now believe was one of the most powerful coronal mass ejections in recorded history. The CME was so fast, so energetic, that it reached Earth in less than 18 hours. That's extraordinary even by today's standards. Most CMEs take 2 to 3 days, but this one crossed the Sun-Earth distance in less than a day, which tells you how much energy was behind it. When it hit Earth's magnetosphere, the impact was visible even to people who had no idea what they were witnessing. Auroras appeared as far south as the Caribbean, as far south as Hawaii. Places that never see the northern lights were bathed in red and green glows bright enough to read by. Telegraph operators reported that their systems were going haywire. Some reported shocks, actual electrical shocks from their equipment. Lines that should have been dead carried current, induced by the geomagnetic storm. In some cases, operators disconnected their batteries and found they could still send messages using only the current induced by the storm itself. If the Carrington event happened, the damage would be significant. Various studies have estimated the economic impact could range from hundreds of billions to potentially over $1 trillion, though these are theoretical projections based on many assumptions. Transformers would be destroyed. It takes months to replace large power transformers, and we don't keep large stockpiles of spares because they're custom-built for specific grid locations. Satellites would be damaged or destroyed by the hundreds. The radiation pulse alone would be enough to fry electronics that aren't specifically hardened against it. GPS would be down globally for an extended period. Communication systems would fail. The internet backbone relies on precise timing signals from GPS. If GPS goes down, large portions of the internet infrastructure start having synchronization issues. Financial markets depend on millisecond-accurate timestamps. Without GPS, high-frequency trading systems would fail. Settlement systems would have problems. But here's what's important to understand. The Carrington Event was a single massive hit. It wasn't a compound event. Earth's magnetosphere wasn't already disturbed when it arrived. It hit us at full strength, but we were at full defensive capacity to absorb it, and even then, even with 1859 technology that was primitive by today's standards, the effects were dramatic and widespread. Now imagine a Carrington-level event arriving during an existing geomagnetic storm. Imagine it hitting when our defences are already engaged. The multiplier effect could push us into territory we've never experienced. Let's bring this closer to the present, on March 13th, 1989, in Quebec, Canada. A geomagnetic storm triggered by a solar eruption caused ground-induced currents in the Quebec power grid. These are currents that get induced in long power lines by the changing magnetic fields during a storm. They flow into transformers and grid infrastructure, causing heating and saturation. In Quebec, the currents were strong enough that circuit breakers started tripping. Grid operators tried to manage the problem, but the cascade happened too fast. Within 90 seconds, the entire Quebec grid collapsed. 6 million people were without power. It was March, still cold, and suddenly there was no heat, no lights, no electricity. It took 9 hours to restore power, and even then some areas were out longer. Transformers had been damaged. The economic cost ran into the hundreds of millions, and businesses lost entire days of operation. And again, that was from a single storm. A powerful one, yes, but standalone. Quebec's grid wasn't already struggling with fluctuations from a previous event. It faced the March 13th storm at full capacity and it still failed. Now think about what happens if a grid is already stressed, if operators are already managing induced currents from an earlier impact, already watching transformers that are running hotter than usual, already dealing with voltage fluctuations, and then a second storm hits before they've stabilized. That's when you go from a regional blackout to a multi-region crisis. That's when recovery times extend from hours to days or weeks. The lesson from history is clear. Compound events are worse than single events by more than just an additive factor. Each historical case we have shows that rapid succession hits produce effects disproportionate to what you'd expect from the sum of the individual events. And each historical case also shows that we're more vulnerable than we think we are. The Quebec grid operators didn't expect their entire system to collapse in 90 seconds. Satellite operators during the Halloween storms didn't expect to lose satellites permanently. Telegraph operators in 1859 didn't expect to be shocked by their own equipment. These were surprises. These were failures that happened despite preparations, despite monitoring, despite professional operators doing their jobs. And here's the uncomfortable truth. Our technology has advanced enormously since 1859, since 1989, even since 2003, but that advancement has also created new vulnerabilities. We have more satellites now than ever before. Thousands of them. Entire constellations providing internet, GPS, communications, weather monitoring, Earth observation, scientific research. Each one is a potential point of failure. We have more interconnected power grids. Electricity flows across state lines, across national borders, in complex patterns managed by sophisticated control systems. That interconnection provides resilience under normal conditions. It allows load balancing and backup supply routes. But it also means that a failure in one region can cascade faster and farther than it could in an isolated system. GPS provides timing signals used by cell phone networks, financial transactions, power grid operations, and internet data routing. Many of these systems have backup timing sources, but GPS remains the primary reference. If GPS becomes degraded, some systems would experience reduced performance while backup systems engage. Your phone might still work for voice calls, but data might slow down. ATMs might have trouble processing transactions. Traffic lights that rely on GPS timing for coordination might fall out of sync. These are second-order effects, failures that happen not because the storm directly destroyed something, but because the storm disrupted a dependency that other systems rely on. So when we look at AR4324 and the current geomagnetic storm in the 48-hour window we're in right now, we're not looking at an isolated curiosity. We're looking at a potential repeat of history, but with higher stakes. We're looking at the possibility of a compound event hitting a more complex, more interconnected, more vulnerable technological civilization than has ever existed before. We've never tested this system under these conditions at this scale, and that uncertainty, that gap in our experience, is part of what makes this a potential black swan. But understanding the threat isn't about scaring you. It's about respecting what's possible. It's about recognizing that the systems we depend on every day, the ones we take for granted, have limits. And when those limits are pushed, when conditions align that we haven't experienced before, outcomes can surprise us. So let's talk about what those outcomes could actually look like. Let's walk through the cascade scenario, not as fear-mongering, but as honest assessment. What would actually happen if AR4324 erupts in the next 48 hours and triggers a compound geomagnetic storm while we're already under pressure? What are we really talking about here? Let's be very clear about what we're discussing here. Solar storms are not existential threats to humanity. Solar storms affect our technology and infrastructure, but Earth itself and human survival are not threatened. Solar storms, even the most powerful ones we've ever recorded, do not threaten the planet itself or the survival of the human species. What they threaten is something more specific and more immediate. They threaten the technological infrastructure that modern life depends on. They threaten systems that have become so integrated into daily existence that most people don't even think about them until they stop working. And in a compound event scenario, where multiple hits arrive in rapid succession during an already disturbed magnetosphere, the damage isn't catastrophic in a Hollywood sense. It's catastrophic in a practical sense. It's disruptive in ways that cascade through society faster than recovery can manage. So let's walk through what could actually happen, step by step, system by system, using what we know from historical events and current vulnerability assessments. And let's be honest about probabilities. Most of what I'm about to describe is possible, not guaranteed. The severity depends on factors we can't predict with certainty, like the exact strength of an eruption if it happens, the speed of any resulting CME, the magnetic orientation when it hits Earth. But possibility is still worth understanding, because black swan events by definition are the ones we're least prepared for precisely because they seem unlikely until they're not. Start with the power grid. This is the most immediate and potentially most serious vulnerability. Electric power grids work by maintaining a constant frequency and voltage across vast networks of transmission lines, substations and transformers. It's a delicate balance. Too much power in the system and frequencies rise. Too little and they drop. Grid operators constantly adjust generation and load to keep everything stable. But during a geomagnetic storm, the changing magnetic fields in Earth's magnetosphere induce currents in the ground. Long transmission lines, especially those running north-south in higher latitudes, act like antennas picking up these ground-induced currents. Those currents flow into transformers, which are the critical components that step voltage up for long-distance transmission, or step it down for local distribution. Transformers are designed to handle alternating current at specific frequencies. They're not designed to handle direct current or slowly varying currents, which is what geomagnetically induced currents look like. When those currents flow into a transformer, they cause something called half-cycle saturation. The transformer core becomes magnetically saturated, which causes it to draw more current, which causes heating. In extreme cases, the heating can damage the transformer's insulation, cause partial melting of internal components, or even lead to complete failure. And here's the problem. Large power transformers are not commodity items. They're not sitting in warehouses waiting to be installed. They're custom-built for specific grid locations based on voltage requirements, cooling specifications, and physical constraints. Building a new large transformer takes months, sometimes over a year. Transporting them is complex because they weigh hundreds of tons and require special rail cars and road permits. If a major geomagnetic storm damages multiple transformers across a region, you're not talking about a quick replacement. You're talking about months of reduced capacity or rolling blackouts while repairs and replacements happen. Now, most grids have protection systems. They monitor for anomalies. Circuit breakers can trip to isolate problems before they cascade. Grid operators can shed load intentionally to prevent overload. Modern grids are far more resilient than they were in 1989 when Quebec went dark, but those protections assume a certain level of disturbance. They're designed for the expected range of problems. A compound geomagnetic storm, where the second hit arrives while the grid is already stressed from managing the first storm, could push conditions outside that expected range. Operators might be dealing with transformers that are already running hot, already showing signs of stress when the second wave of induced currents arrives. That's when protective systems might not be enough. That's when you move from managed disruption to cascading failure. And power isn't isolated. Everything else depends on it. Communication systems have battery backup and generators, but those are designed for temporary outages measured in hours, maybe a day or two. If power is out for a week, cell towers start going dark as their backup systems run out of fuel or battery capacity. Internet backbone nodes have similar limitations. Your home internet might work for a while on battery backup if your router has one, but the infrastructure upstream needs power too. Within days of widespread power outages, communication networks start degrading, and when communication goes down, coordination of recovery efforts becomes harder. Repair crews can't coordinate efficiently. Supply chains can't track shipments. The cascade deepens. Then there are satellites. Right now, there are thousands of active satellites orbiting Earth. They provide GPS, communications, weather monitoring, Earth observation, scientific research, military reconnaissance, and increasingly internet connectivity. Every satellite is vulnerable to space weather to some degree. The radiation environment during a severe geomagnetic storm increases dramatically. High-energy particles can penetrate satellite shielding and cause what's called a single event upset, where a particle hits a memory chip or processor and flips a bit, causing a software error. Most of the time, these are minor. The satellite's software detects the error and corrects it. But during intense storms, the rate of these events goes up. Multiple. Errors can compound. Systems can crash. Satellites can go into safe mode, shutting down operations until the radiation environment calms. In a compound storm scenario, where satellites are already dealing with elevated radiation from the first event and then get hit with a second wave before they've fully recovered, the probability of permanent damage goes up. Solar panels can degrade, electronics can fail permanently, satellites can be lost. During the Halloween storms of 2003, multiple satellites were damaged and some were lost entirely, and that was with the satellite population and our dependency on them being a fraction of what it is now. Imagine losing a significant percentage of GPS satellites. The system is designed with redundancy, but if enough satellites go offline, coverage becomes spotty. Accuracy drops. In some regions, GPS might become unreliable or unavailable. And as I mentioned earlier, GPS isn't just navigation, it's timing. It's synchronization for systems across the economy. Aviation is another sector that's more vulnerable than most people realize. Polar routes, the flight paths that go over or near the North and South Poles, are the most efficient paths for long-haul flights between certain city pairs. Flying from New York to Hong Kong or Los Angeles to Dubai often means routing near the poles. But during geomagnetic storms, those high-latitude regions experience increased radiation exposure. For a single flight, the increased dose isn't catastrophic, but it exceeds safety limits set by aviation authorities and radiation protection guidelines. So during severe storms, airlines have to reroute flights away from the poles. Those reroutes add flight time, burn more fuel, sometimes require refueling stops that weren't planned. It's disruptive and expensive. And in a compound storm scenario where the radiation environment stays elevated for days instead of hours, those disruptions multiply. Schedules fall apart. Passengers get stranded. Cargo gets delayed. And then there are the second-order effects that most people never think about. Modern supply chains operate on just-in-time principles. Inventory is minimized. Components arrive when they're needed, not weeks in advance. That efficiency depends on reliable transportation, reliable communication, and reliable tracking systems. If GPS goes down, if power is intermittent, if communications are disrupted, supply chains start breaking down. Factories can't get the parts they need. Stores can't restock shelves as fast as they normally do. It's not that everything stops immediately. It's that the system starts operating less efficiently, and those inefficiencies compound. Within days, shortages start appearing. Within weeks, if the disruptions continue, the economic impact becomes severe. Financial systems are another vulnerability. Stock markets, banking transactions, credit card payments, all of these depend on precise timing and reliable communication. High-frequency trading, which accounts for a significant portion of market volume, relies on millisecond-accurate timestamps. Those timestamps come from GPS. If GPS is down or unreliable, trading systems have problems. They might halt trading entirely as a safety measure to prevent errors. Markets could be closed for hours or even days while systems are verified and restored. And while that's happening, economic uncertainty spikes. People can't access their money if ATMs are down and bank systems are offline. Businesses can't process payments. The longer it goes on, the more the economic impact grows. Now let me be very clear again. This is not about panic. This is not about predicting that everything I just described will definitely happen. The probability of the absolute worst-case scenario, where everything fails simultaneously and stays failed for weeks, is low. Even in a compound storm event, most systems have redundancies, most operators have procedures, most infrastructure has been hardened to some degree, based on lessons from past events. The lights will most likely stay on. GPS will most likely keep working, maybe with some temporary degradation. Satellites will most likely survive, with only a small percentage experiencing failures. But the point is that we don't know for certain. We don't have experience with a compound geomagnetic storm at scale hitting the modern technological infrastructure we've built over the last 2 decades. We have models and simulations that suggest we'll be okay, that the damage will be limited and manageable. But models are based on assumptions, and assumptions can be wrong when conditions fall outside the expected range. That's the nature of black swan events. They're the scenarios where the models don't capture reality because reality is doing something the models didn't anticipate, and the consequences of being wrong, of underestimating the vulnerability, are significant enough that they deserve attention. If a compound storm from AR4324 erupting during the current geomagnetic disturbance does produce cascading failures, even limited ones, even regional ones, the recovery timeline extends. Damaged transformers take months to replace. Permanently lost satellites can't be relaunched overnight. Supply chain disruptions have momentum. They don't stop instantly when the storm ends. The economic impact of even a week-long disruption across multiple sectors would be measured in billions of dollars. A month-long disruption would be tens of billions or more. And the human cost, the inconvenience and hardship for millions of people dealing with power outages, communication failures, and service disruptions, that's not captured in economic estimates. So when we talk about what could happen, we're talking about a range of possibilities. At the mild end, we see some additional auroras, some temporary communication disruptions, some satellite operators scrambling to manage their systems, and everything returns to normal within a day or two. At the severe end, we see power outages affecting millions, satellite losses affecting GPS and communications for weeks, cascading supply chain failures, and economic impacts that take months to fully resolve. Most likely we'd land somewhere in the middle if AR4324 erupts and triggers a compound event. Serious disruptions in certain sectors, manageable but noticeable impacts for the general public. A reminder that we're more dependent on stable space weather than we usually acknowledge. But the question isn't really about predicting the exact outcome. The question is whether we're prepared for the range of possibilities, and the honest answer is that our preparedness is built mostly for single event scenarios during non-disturbed conditions. We're less prepared for compound events. We're less prepared for rapid succession hits that don't give systems time to recover between impacts. And that gap in preparedness is exactly what makes this a potential black swan. It's the scenario we haven't fully tested, haven't fully planned for, haven't fully built redundancies against. And that's why scientists are watching AR4324 so closely right now. That's why the next 48 hours matter. Because this is the window where we find out whether the convergence of factors stays theoretical or becomes real. So let's talk about what scientists are actually monitoring, what they're looking for, and how they're tracking this potential threat in real time. While you're going about your day, while you're working or eating or watching this video, there are teams of scientists and forecasters around the world who are not taking their eyes off the sun. This isn't a casual observation. This is a focused 24/7 watch operation, and it's been running continuously since the space age began. The NOAA Space Weather Prediction Center in Boulder, Colorado, is the United States' primary hub for monitoring and forecasting space weather. They operate around the clock, every single day, with trained forecasters analyzing data from multiple spacecraft and ground-based instruments. And right now, today, AR4324 is one of their primary focuses. The tools available to these scientists are remarkable. We have spacecraft positioned at different points around the Sun-Earth system, each providing a unique perspective. The Solar Dynamics Observatory, SDO, sits in orbit around Earth and watches the Sun continuously in multiple wavelengths of light. It can see things human eyes can't see, ultraviolet and extreme ultraviolet light that reveals the Sun's atmosphere and magnetic structures in exquisite detail. Every image SDO sends back shows active regions, flares as they erupt, prominences lifting off the surface, the constant churning motion of plasma flowing along magnetic field lines. When scientists look at AR4324, they're using SDO data to see its magnetic structure, to watch how it's evolving, to spot changes that might indicate an eruption is building. Then there's SOHO, the Solar and Heliospheric Observatory, a joint project between NASA and European agencies that's been watching the Sun since the mid-1990s. SOHO carries an instrument called a coronagraph, which is essentially a telescope that blocks out the bright disk of the Sun so you can see the much fainter corona, the Sun's outer atmosphere that extends millions of miles into space. This is where coronal mass ejections become visible. When a CME erupts, it appears in SOHO's coronagraph images as a bright cloud expanding outward from the Sun. By tracking that cloud over multiple images, scientists can calculate its speed, its direction, and whether it's heading toward Earth. SOHO is how we knew the New Year's Eve CME was coming. It's how we'll know if AR4324 erupts and launches another one. There are other spacecraft too. STEREO, the Solar Terrestrial Relations Observatory, consists of 2 spacecraft that orbit the Sun at different positions than Earth. They provide side views of solar eruptions, which helps with determining the 3-dimensional structure of CMEs. If a CME erupts off the Sun's surface, STEREO can see it from an angle that helps confirm whether it's heading toward Earth or off into some other direction in space. The combination of these different perspectives, SDO watching the Sun's face, SOHO watching the corona, STEREO watching from the side, gives scientists a comprehensive monitoring system. But watching is only part of the job. The harder part is interpretation. The Sun doesn't announce its intentions. There's no alarm that goes off saying a flare is about to happen. Forecasters look for patterns, for changes in magnetic structures, for signs that energy is building to unstable levels. One of the key things they watch is the magnetic configuration of active regions. That beta-gamma designation I mentioned earlier for AR4324, that's a classification that indicates magnetic complexity. Beta means there are opposite magnetic poles mixed together. Gamma means the magnetic neutral line, the boundary between opposite poles, is complex and irregular. All of that complexity means energy is stored. It means the magnetic field is twisted and stressed, and it means the region is capable of producing powerful flares. But capability doesn't mean certainty. Plenty of complex active regions simmer and churn and then fade without ever producing a major eruption. Some do erupt, but only with smaller flares. Predicting exactly when and how strong an eruption will be is still beyond our ability. The Sun is turbulent, chaotic, driven by plasma flows and magnetic fields interacting in ways that are difficult to model precisely. So when forecasters issue watches or warnings, they're dealing in probabilities. They can say that a region like AR4324 has a significant probability of producing M-class or X-class flares over the next few days. They can say that if a flare happens, there's a chance it will launch a CME, but they can't tell you that it will definitely happen at a specific time. That uncertainty is frustrating, but it's also honest. Science doesn't always give you clean predictions. What it gives you is the best assessment based on current data. And right now, the assessment is that AR4324 is a region worth watching closely. Its magnetic complexity is high. Its position is Earth-facing. It's active, with smaller flares already having occurred. The combination of those factors means the probability of a significant eruption over the next 48 to 72 hours is higher than baseline. Not guaranteed, but higher. And in the context of Earth already being under storm conditions from the New Year's Eve CME, that elevated probability is what makes this a watch situation. So what specifically are scientists looking for as this watch continues? They're looking for changes in the magnetic field structure. Magnetic fields on the Sun can be measured using something called the Zeeman effect, where magnetic fields split spectral lines in characteristic ways. By analysing the light coming from an active region, scientists can map the strength and orientation of the magnetic field. If they see the field becoming more sheared, more twisted, more compressed, those are signs that energy is building. If they see the neutral line, that boundary between opposite poles, becoming more complex or irregular, that's another indicator of instability. They're also watching for filament eruptions. Filaments are structures of cooler, denser plasma suspended in the Sun's hot corona, held in place by magnetic fields. When the magnetic field becomes unstable, filaments can erupt, lifting off the surface and sometimes triggering or accompanying flares and CMEs. If scientists see filaments over AR4324 starting to rise or show signs of instability, that could be a precursor to a larger eruption, and they're monitoring the rate of smaller flares. Active regions often produce a series of smaller eruptions before a major one. It's not a perfect rule, But if AR4324 starts firing off more frequent or stronger flares, that could indicate that the magnetic energy in the region is increasing and looking for release. Each small eruption is like a tremor before an earthquake. Not every tremor leads to the big one, but a cluster of tremors gets attention. Another aspect of the watch is tracking the sunspot's position on the solar disk. The sun rotates, and from Earth's perspective, sunspots appear to move across the sun's face from east to west over about 2 weeks. AR4324 is currently in a position where it's facing Earth. That's the danger zone. If it's going to erupt in a way that affects us, now is the time. In a few days, the sun's rotation will carry AR4324 toward the western edge of the disk from our viewpoint. An eruption then would be less likely to send a CME directly at Earth because the angle would be off. And a week from now, AR4324 will be on the far side of the sun, completely out of view and no longer a direct threat to Earth, even if it does erupt. So the 48 to 72 hour window we're in right now is the critical period. It's when the geometry is worst for us, when an eruption has the highest probability of sending a CME on a collision course with our planet. But there's another factor that makes this watch more complex. Sunspots can produce multiple eruptions. It's not like a volcano that erupts once and then goes dormant for years. A magnetically complex active region can erupt multiple times over several days as different parts of the magnetic structure become unstable and release energy. So even if AR4324 erupts tomorrow and launches a CME, that doesn't mean the watch is over. It could erupt again and again. Each eruption is an independent event, a roll of the dice on direction, speed, and strength. During the Halloween storms of 2003, the same active regions erupted multiple times over the span of 2 weeks, each time launching new CMEs, some of which hit Earth and some of which missed. That possibility of multiple eruptions is part of what makes this situation particularly concerning in the context of the current geomagnetic storm. If AR4324 erupts once and sends a CME toward Earth that arrives in a day or two, that's already a compound event scenario because Earth is still disturbed from the New Year's Eve impact. But if AR4324 erupts multiple times over the next few days, launching several CMEs in quick succession, we could be looking at a barrage similar to the Halloween storms, each CME arriving while Earth is still reeling from the previous one. That's when you really start to see cascading effects, when systems don't have time to recover between hits, when each impact lands on an already weakened magnetosphere. And this is where forecasting becomes as much art as science. Models can predict CME arrival times within a range, usually plus or minus 6 to 12 hours depending on the speed and other factors. Models can estimate the strength of the resulting geomagnetic storm based on the magnetic orientation of the CME when it hits Earth. But there's always uncertainty. There are always factors that can't be perfectly captured. So when forecasters issue watches or warnings, they're giving you their best assessment with the understanding that reality might deviate from the prediction. What does this mean for you, for someone watching this video and wondering what to actually pay attention to? It means the next 2 days are the critical window. It means that if AR4324 is going to erupt in a way that creates a compound storm scenario, it will most likely happen while the sunspot is still facing Earth, which is right now through roughly January 4th. After that, the angle becomes less direct and the threat diminishes. It means that if you want to follow this in real time, there are public resources available. NOAA's Space Weather Prediction Center has a website where they post forecasts, alerts, and current conditions. You can see the latest images of the sun. You can read forecaster discussions where they explain what they're seeing and what they expect. It's all free, it's all public, and it's all updated continuously. So the watch is on, scientists are monitoring, data is flowing in from spacecraft every few seconds, forecasters are analyzing, and everyone involved is wondering the same thing you are. Will AR4324 erupt? And if it does, how strong will it be, and will it hit us? Those questions don't have answers yet. But the fact that the questions are being asked by professionals who do this for a living tells you that this is not a routine moment. This is a convergence of factors that deserves attention, and whether the sunspot erupts or not, whether this turns into a black swan event or just another near miss, the lesson is clear. We live with a dynamic star, and understanding what that means, understanding why the next 48 hours matter is the first step toward being prepared for a future where space weather events like this become more common. So let's talk about that convergence, about why this specific moment in time is different from other solar watches. It's easy to hear about a big sunspot and think, okay, that's interesting, but the sun has had big sunspots before. It's easy to hear about a geomagnetic storm and think, well, We get those sometimes, and we manage. It's easy to dismiss any single factor as routine, as something we've dealt with before, as something that's not worth worrying about. And in isolation, each of those factors is routine. We do see large sunspots regularly during solar maximum. We do experience geomagnetic storms multiple times a year. We do monitor active regions and track CMEs and issue watches. It happens. It's part of living on a planet orbiting an active star. But what's not routine is when all of these factors align at the same time. What's rare is when multiple risks overlap in a narrow window, each amplifying the others, creating a compound threat that's greater than the sum of its parts. And that's exactly what we're looking at right now. This isn't about one thing going wrong. It's about several things happening simultaneously, and the specific combination of those things is what transforms a routine space weather event into a potential black swan. Let's break down the convergence. Factor 1 is AR4324 itself. This is a large, magnetically complex active region with a beta-gamma delta magnetic structure. That structure indicates stored energy and instability. It means the sunspot is capable of producing powerful eruptions. Regions like this don't appear every day. During solar minimum, the quiet years of the 11-year cycle, the sun can go weeks or even months without any significant active regions. Even during solar maximum, when the sun is most active, truly complex beta-gamma delta regions are only present a fraction of the time. So the existence of AR4324 with this level of complexity is the first factor. It's not common, but it's not unheard of either. Factor 2 is the sunspot's position. Right now, AR4324 is facing Earth. The sun rotates, and active regions move across the sun's face from our perspective. There's a window of roughly a week when an active region is in the danger zone, when an eruption would send a CME directly toward us. Before that window, the region is still rotating into view, and eruptions would be angled away. After that window, the region rotates out of view toward the sun's far side. We're in the middle of that window right now. AR4324 is pointed at us. If it erupts, the geometry is worst case for Earth. That's the second factor, positioning. And again, in isolation, this isn't unusual. Every active region spends about a week facing Earth as the sun rotates. But combined with the first factor, a complex unstable region that's also Earth-facing, the risk starts to increase. Factor 3 is the timing relative to Earth's magnetosphere. This is where things get more unusual. Earth is currently under geomagnetic storm conditions from the New Year's Eve CME impact. Our magnetosphere is compressed. The particle populations inside the magnetosphere are enhanced. The whole system is stressed. That state of disturbance makes us more vulnerable to a second impact. It's like having your shield already damaged when the next attack comes. If AR4324 erupts and sends a CME toward Earth in the next 48 hours, that CME would arrive while we're still recovering from the first storm. The compound effect would be worse than either storm individually. And this combination, a complex active region erupting while Earth is already disturbed, is much rarer. It requires not just an active sun but specific timing. The previous CME has to have happened recently enough that Earth is still affected, and the next eruption has to happen before we've recovered. That window is narrow, maybe 3 to 4 days. We're in it, right now. Factor 4 is the broader solar cycle context. We're in solar maximum of cycle 25. The sun's overall activity level is elevated. There are more active regions, more flares, more CMEs, more solar wind variability. The background conditions are more turbulent. That elevated activity increases the probability that any given active region will erupt. And it also means that the solar wind environment between the sun and Earth is more disturbed than it would be during solar minimum. CMEs travelling through a disturbed solar wind can be accelerated or have their magnetic structures altered in ways that affect how they impact Earth. So the solar cycle context is another factor. It's not deterministic, but it shifts the probabilities. Now, take all 4 factors together. A magnetically complex sunspot positioned directly facing Earth, active during a period when Earth's magnetosphere is already under storm conditions occurring during solar maximum when background activity is elevated. Each factor amplifies the others. The complexity of the sunspot increases the probability of a strong eruption. The positioning means that eruption would be aimed at us. The timing means the impact would hit us while we're vulnerable. And the solar cycle context means the overall environment is more unstable. This is the convergence. This is why the next 48 hours matter in a way that most solar watches don't. And here's the statistical reality. Convergences like this are rare. You need specific timing for the magnetospheric disturbance to overlap with the sunspot's Earth-facing window. You need the sunspot to be complex enough to pose a threat. You need the solar cycle to be in an active phase. Any one of these factors is common enough during certain periods. 2 of them overlapping is less common but still happens occasionally. 3 factors aligning is unusual. All 4 at once is the kind of scenario that happens maybe a few times per solar cycle, if that. And when it does happen, the risk profile changes. You're no longer dealing with routine space weather. You're dealing with a potential compound event where the outcome is harder to predict because we have less historical data on this specific combination of conditions. And this is exactly what defines a black swan event in the context of space weather. It's not impossible. It's not outside the laws of physics. Everything about this scenario is understood scientifically. We know how sunspots work. We know how CMEs propagate. We know how geomagnetic storms affect Earth. What makes it a black swan is the rarity of the convergence, and the fact that our systems, our infrastructure, our preparedness plans are built mostly around more common scenarios. We've hardened satellites against typical radiation levels. We've designed power grids to handle typical geomagnetic disturbances. We've built redundancy into GPS for typical satellite failures. But compound events test the edges of those typical ranges. They push systems into conditions they weren't specifically designed for. And that's where surprises happen. That's where the unexpected failures occur. So if even 2 of these factors aligned, scientists would be paying attention. If we had a complex sunspot facing Earth during normal magnetospheric conditions, there would be watches issued and monitoring intensified. If we had a geomagnetic storm ongoing and a new active region rotating into view, forecasters would be tracking it. But having all 4 factors converge in the same 48-hour window, that's what elevates this from interesting to urgent. That's what makes this a potential black swan scenario worth discussing, worth understanding, worth watching closely. And let me be clear about what I'm not saying. I'm not saying that AR4324 will definitely erupt. Active regions can remain stable and fade without producing major flares. I'm not saying that if it does erupt, the CME will definitely hit Earth. Eruptions can send CMEs in directions that miss us entirely. I'm not saying that if a CME does hit during the current geomagnetic disturbance, it will definitely cause catastrophic damage. Most of the time, even in compound scenarios, our systems hold. What I am saying is that the convergence of factors right now creates a higher probability of a serious compound event than we normally face. The odds have shifted. The dice are loaded slightly more toward an outcome that would be disruptive and difficult to manage, and in risk assessment, probability matters. Even if the chance of the worst-case scenario is low, if the consequences of that scenario are severe enough, it's worth paying attention. That's why we have insurance. That's why we have emergency plans. That's why forecasters issue watches even when the probability of impact is only moderate. Because understanding space weather risks helps us build more resilient infrastructure and respond appropriately when events do occur. So the next 48 hours are the window. This is the period when AR4324 is in optimal position for a direct Earth impact if it erupts. This is the period when Earth's magnetosphere is still recovering from the New Year's Eve storm and thus most vulnerable to a second hit. This is the period when all 4 factors are aligned. After this window closes, either because AR4324 rotates out of the danger zone or because Earth's magnetosphere recovers, the risk profile drops back toward normal. We'll still watch the sunspot, we'll still monitor space weather, but the specific convergence that creates black swan potential will have passed. So what happens now? What should you be watching for? And what does the next few days look like as this situation plays out? Let's talk about the practical side of this watch, about what you can monitor yourself and what to expect as the 48th hour countdown continues. So you understand the threat, you understand the convergence, you understand why the next 48 hours matter. Now the question becomes practical. What actually happens next? What should you be watching for? What will the sequence of events be if AR4324 does erupt, and what does it mean for you personally? Let's walk through the timeline and the indicators so you know what to look for and what it means. If AR4324 erupts with a significant flare, the first thing that happens is an X-ray flash. Flares release energy across the electromagnetic spectrum, but the X-ray and extreme ultraviolet portions of that spectrum travel at the speed of light. That means they reach Earth in 8 minutes. That's how long it takes light to travel from the Sun to our planet. So from the moment of eruption to the moment Earth's upper atmosphere absorbs that X-ray energy, 8 minutes. And the effects of that X-ray absorption are immediate. The Earth's ionosphere, the layer of atmosphere, where UV radiation from the sun ionizes atoms and creates charged particles, suddenly gets a massive dose of additional ionization. That changes how radio waves propagate through the ionosphere. For high-frequency radio, the kind used for long-distance shortwave communication, that sudden ionization causes absorption. The radio waves get absorbed instead of reflected, and communication gets disrupted. Radio operators call this a radio blackout. It affects primarily the sunlit side of Earth, the side facing the sun when the flare happens. The blackout can last from minutes to hours depending on the strength of the flare. GPS signals can also be affected because they travel through the ionosphere, and changes in ionization cause delays and errors in the signal. So within 8 minutes of a major flare from AR4324, we'd see radio disruptions and GPS degradation. But the flare itself, the X-ray flash, isn't the main threat. It's disruptive, but temporary. The main threat is whether the eruption launches a coronal mass ejection. That determination takes longer. Scientists watch the coronagraph, images from SOHO and other spacecraft. A CME appears as a bright expanding cloud in those images, erupting outward from the sun's surface. It usually takes 1 to 4 hours after a flare before the CME becomes clearly visible in coronagraph data, because the CME has to travel far enough from the sun's bright disk to be seen in the coronagraph's field of view. So there's a waiting period. The flare happens, radio blackouts occur, and then over the next few hours scientists are watching coronagraph images to see if a CME is present, how fast it's moving, and what direction it's heading. If the CME is aimed at Earth, trajectory analysis takes several more hours. Scientists measure the CME's speed from multiple images over time. They measure its angular width, how much of the sky it covers as seen from the spacecraft. A CME that's heading directly toward Earth appears as a halo, a ring expanding in all directions around the sun, because you're looking straight into the oncoming cloud. That halo signature is a key indicator. If forecasters see a halo CME following an eruption from an Earth-facing active region, that's high confidence that we're going to get hit. The question then becomes when and how hard. CME speeds vary widely. Slow ones travel at a few hundred miles per second and take 3 to 4 days to reach Earth. Those are less concerning because the slower speed usually correlates with less energy. Fast ones can travel at several million miles per hour, and the fastest on record have made the journey in less than a day. The Halloween storms included CMEs that reached Earth in about 15 to 18 hours. The Carrington Event CME in 1859 arrived in less than 18 hours, so if AR4324 produces a fast CME, we could be looking at impact within a day. That's not a lot of time to prepare, but it's enough to issue warnings, alert operators of critical infrastructure, and take mitigation measures. Once the CME speed and direction are confirmed, forecasters issue a geomagnetic storm watch or warning. A watch means conditions are favourable for a storm within the next few days. A warning means a storm is likely or already occurring. Those alerts go out to power companies, satellite operators, airlines, and anyone else who needs to know. And then it's a waiting game. The CME travels through space. We watch its progress with spacecraft upstream of Earth that can detect the CME before it actually hits our magnetosphere. When the CME arrives, usually within a window of 12 to 72 hours depending on speed, that's when the geomagnetic storm begins. And this is where the compound scenario plays out. If AR4324 erupts in the next 48 hours and launches an Earth-directed CME, that CME will arrive while Earth is still under storm conditions from the New Year's Eve impact. The current geomagnetic disturbance is expected to persist through January 3rd, possibly into the 4th. A fast CME launch today or tomorrow would arrive during that window. And as I've explained, the second impact landing while the magnetosphere is still compressed and disturbed from the first is what creates the compound threat. The effects amplify, the damage potential increases, the risk of cascading failures goes up. So what can you do with this information? What can you monitor yourself if you want to follow this in real time? First, NOAA's Space Weather Prediction Center website is your best resource. They post updates multiple times a day. They have a section for current space weather conditions that shows geomagnetic storm levels, solar radiation levels, and radio blackout conditions. They have forecaster discussions where the scientists explain what they're seeing and what they expect, and they have alerts that list any watches or warnings currently in effect. It's all free, it's all public, and it's written in language that's mostly accessible, even if you're not a scientist. Second, if you want to see solar images and check on AR4324 yourself, NASA's Solar Dynamics Observatory has a public website where they post near real-time images of the sun in multiple wavelengths. You can actually see the sunspot, see flares as they happen, see the structure of the sun's magnetic field. It's remarkable how much data is publicly available. You don't need special access, you don't need to be an insider. The information is there. Third, if you're interested in auroras, there are aurora forecast websites and apps that predict when and where auroras will be visible based on current geomagnetic conditions. If the compound storm scenario plays out and we do get a significant second geomagnetic storm from an AR4324 eruption, auroras could be visible at unusually low latitudes. People in northern United States, southern Canada, northern Europe, these regions that occasionally see auroras during strong storms, you might get a show. It's one of the few positive aspects of geomagnetic storms. The auroras are beautiful. They're nature's reminder that we live in a connected system, that the sun and earth are in constant interaction. But beyond monitoring, what should you actually do? Should you be stockpiling supplies? Should you be preparing for blackouts? The honest answer is probably not, unless you live in a region that's particularly vulnerable. Most people don't need to take dramatic action. The most likely outcome, even if AR4324 does erupt and even if we do get a compound storm, is that you'll experience some minor inconveniences. Maybe GPS is a little less accurate for a few hours. Maybe you see some news reports about satellite operators dealing with anomalies. Maybe power companies issue statements that they're monitoring grid conditions closely. For the vast majority of people, life will continue normally. But it doesn't hurt to have basic preparedness in place. If you live in a region where power outages are possible, having flashlights, batteries, some non-perishable food and water on hand is sensible regardless of space weather. If you rely heavily on GPS for navigation, maybe have a backup plan, like old-fashioned maps or written directions just in case. If you're travelling by air over polar routes in the next few days, be aware that flights might be delayed or rerouted if geomagnetic conditions worsen. These are common-sense measures that don't require panic, just awareness. And here's the most important thing to understand. The most likely outcome is that nothing dramatic happens. Most active regions don't produce catastrophic eruptions. Most geomagnetic storms are manageable. Most of the time, even when conditions look concerning, the worst-case scenario doesn't materialize. AR4324 might simmer and churn for another few days and then fade without producing a major flare. Or it might erupt, but the CME might miss Earth entirely. Or the CME might hit, but the magnetic orientation might be such that the geomagnetic storm is moderate rather than severe. There are many pathways where this ends up being a non-event, where a week from now we look back and say, well, that was interesting, but nothing happened. And that's okay. That's actually the best outcome. But the reason we watch, the reason we monitor, the reason we talk about these possibilities is because the alternative, the scenario where we don't pay attention and then get surprised by a serious compound event, that alternative is worse. It's better to be prepared and not need it than to need it and not be prepared. It's better to understand the risk, even if the risk doesn't materialize, than to be blindsided by something we could have seen coming. So over the next 48 to 72 hours, watch the news. Check the Space Weather Prediction Center website if you're curious. See if there are any alerts or warnings issued. See if AR4324 erupts. And if it does, see what happens next. Track the CME. See if it's aimed at Earth. See when it's forecast to arrive. And then see how Earth responds. It's an opportunity to learn, to observe, to understand how our planet interacts with its star. And whether this turns into a black swan event or just another routine watch that ends quietly, the knowledge you've gained from understanding the scenario is valuable. Because this won't be the last time we face a potential convergence like this. The sun is dynamic. We're in solar maximum. More active regions will appear, more eruptions will happen. And the more we understand about how these events unfold and what they mean, the better prepared we'll be for the next one. So let's talk about that bigger picture, about what this moment teaches us regardless of the outcome. Step back for a moment from the specifics of AR4324, from the 48-hour countdown, from the geomagnetic storm and the convergence of factors. Step back and look at the bigger picture, because this moment, regardless of how it resolves, is teaching us something important about the world we live in. We live on a planet that orbits a star, and that star is not stable. It's not a fixed light source that just sits there burning at the same level year after year. It's dynamic, it's active, it's constantly changing, constantly erupting, constantly throwing energy and material out into space. And we, here on Earth, we're living in that star's atmosphere, essentially. The sun's influence extends far beyond its visible surface. The solar wind fills the entire solar system. We're swimming in it. For most of human history, that didn't matter much. The sun rose, the sun set. It provided light and warmth. Occasionally there were unusual auroras that people didn't understand, strange lights in the sky that seemed mystical or ominous. But there were no satellites to worry about, no power grids to protect, no GPS to lose. The sun's variability affected us, but in ways we couldn't perceive. It wasn't until we started building technological civilization, especially in the last century with the advent of radio, then satellites, then our modern interconnected digital infrastructure. It wasn't until then that we became vulnerable to space weather in ways that actually matter to daily life. And now we're in a situation where we depend utterly on systems that are vulnerable to the sun's activity. Every phone in your pocket relies on satellites for GPS. Every flight you take relies on communication systems that can be disrupted by solar storms. Every light in your house depends on a power grid that can be affected by geomagnetic disturbances. We've built a civilization that's exquisitely sensitive to space weather, and we've done it mostly without thinking about that sensitivity because for decades we've been lucky. We've had solar storms, yes, but none have been catastrophic. We've had near misses, close calls, events that could have been worse. But we haven't had the big one, the once-in-a-century event that tests everything to its limits. The Carrington Event in 1859 is our closest historical reference, and it happened before the modern world existed. If it happened today, the damage would be staggering. But because it didn't happen in living memory, because most people have never experienced a truly severe space weather event, the threat feels abstract. It feels abstract because most people haven't experienced a major space weather event in their lifetime, and that's the psychology of black swan events. They're rare enough that we don't build our lives around preparing for them. We focus on the everyday threats, the routine problems, the things we know from experience are likely to happen, and that's rational most of the time. You can't live in constant fear of the improbable, but the improbable is not the same as impossible, and when we're talking about the sun, we're not talking about some speculative threat that might never materialize. We're talking about an activity cycle that we know exists, that we can measure, that we've observed for centuries. We know the sun goes through periods of high and low activity roughly every 11 years. We know that during solar maximum, the sun is more likely to produce powerful eruptions. We know that compound events, where multiple CMEs hit Earth in succession, have happened before and will happen again. The only question is when, and whether we're prepared when it does. And this is where AR4324 and the current moment become valuable, regardless of whether the sunspot erupts. Because this is a teaching moment. This is an opportunity for people to understand that space weather is real, that it affects us, that the sun is not a stable background element but an active participant in our environment. Every time we go through a watch like this, every time we track a potentially dangerous active region, we build awareness, we build knowledge, we build cultural memory that space weather matters, and that awareness is valuable because it drives preparedness. Infrastructure doesn't get hardened against geomagnetic storms because some bureaucrat decided it was a good idea. It gets hardened because there's public understanding that the threat is real, which creates political will, which creates funding, which creates engineering requirements. Satellites don't get built with radiation shielding just for fun. They get that shielding because operators know that space weather can damage or destroy satellites, and that knowledge comes from past events, from failures, from near misses, from moments like this where we watch and learn. So whether AR4324 erupts or not, whether this becomes a black swan event or a routine watch that ends quietly, we're gaining something. We're gaining understanding. We're gaining data. We're gaining awareness. And that makes us incrementally more prepared for the next time. Because there will be a next time. The sun will be active again. There will be other complex sunspots. There will be other geomagnetic storms. There will be other moments where conditions converge in concerning ways. That's guaranteed. The sun cycle doesn't stop. What's not guaranteed is whether we'll use these moments to prepare, to improve, to build resilience into our systems. And here's the hopeful part. We can do this. We can build a civilization that's resilient to space weather. We know how to harden power grids against geomagnetic disturbances. We know how to design satellites that can survive radiation storms. We know how to create redundancy in GPS and communication systems. The technology exists. The engineering knowledge exists. What's often lacking is the funding and the political will to implement it everywhere it's needed. And that comes from awareness. It comes from moments where people realize, oh, this is actually a real threat. This matters. We need to take it seriously. So when you watch the news over the next few days, when you check the Space Weather Prediction Center website, When you see updates about AR4324, you're participating in that awareness, building, you're learning, you're understanding, and that understanding ripples outward. You tell someone else, they become aware, they share it, awareness grows, and eventually that awareness translates into action, into better infrastructure, into more resilient systems, into a civilization that can weather space weather events without catastrophic failures. And let's be honest about what that looks like. We're not going to eliminate vulnerability entirely. We're not going to build a perfect shield that makes us immune to solar storms. That's not realistic. What we can do is reduce vulnerability to the point where even severe events are manageable disruptions, rather than civilization-threatening disasters. We can build redundancy so that if one satellite fails, others take over. We can design power grids with protections so that transformers don't melt even during severe geomagnetic storms. We can create backup systems for GPS so that if the primary constellation is degraded, alternative navigation methods are available. We can build resilience, and resilience is not the same as invulnerability. Resilience means you get hit, you bend, but you don't break. You recover, you adapt, you learn from each event and come back stronger. That's the trajectory we need to be on. Not panicking about the sun, not building bunkers and hoarding supplies as if the end is near, but calmly, rationally, building systems that can handle the rare events, the black swans, the convergences that we know will happen eventually even if we can't predict exactly when. So here we are, January 2nd, 2026. A giant sunspot facing Earth, a geomagnetic storm is already in progress, a 48-hour window where conditions could align to create something serious. And whether that something happens or not, whether this is a black swan moment or just another day in the life of a planet orbiting an active star, you now understand what's at stake. You understand science, you understand the risks. You understand why scientists are watching. You understand what could happen and what's more likely to happen. And you understand that living with a dynamic star means accepting some level of uncertainty, some level of risk, while also building the knowledge and the infrastructure to manage that risk as well as we can. That's the bigger picture. That's the lesson. The sun is not our enemy. It's our life source. Without it, Earth would be a frozen dead rock. But the sun is also not our servant. It doesn't care about our satellites or our power grids or our GPS networks. It does what stars do. It burns. It erupts. It throws energy into space. And we, as the intelligent inhabitants of a planet in that star's domain, we have to learn to live with that reality. We have to learn to watch the sun, to understand it, to predict it as best we can, and to build our civilization in a way that can survive the moments when the sun reminds us how powerful it really is. So stay curious, stay informed, keep learning. Whether you're watching this video because you're fascinated by space science or because you're concerned about what this means for your daily life, the knowledge you've gained here matters. Share it, talk about it, help build that cultural awareness that space weather is real and relevant. And the next time you see an aurora, the next time you hear about a solar storm, the next time there's a watch for a potentially dangerous sunspot, you'll understand what's happening, you'll know why it matters, and you'll be part of a society that's learning slowly but surely to live wisely with the star that gives us everything. If you found this valuable, if understanding this threat and this moment mattered to you, then help this information reach more people. Subscribe so you get updates if this situation develops further. Like this video so the algorithm knows this is content worth sharing. And drop a comment telling me where you're watching from and whether you'll be keeping an eye on AR4324 over the next few days. Because we're all in this together. We all live under the same sun. And together, by understanding and preparing, we make ourselves more resilient to whatever that sun decides to throw at us next. Stay safe, stay informed, and keep watching the sky.